Good afternoon. This is CIVE 638, Sedimentation Engineering. This is class number 151. That's 15-week first class of 2 classes per week. And I'm Professor Victor Ponce from the Department of Civil Engineering at San Diego State University. The subject today is calculations of scour, bridge scour. We're going to use the calculators. We have several calculators for this purpose. So we're going to be looking at over here. I believe we're over here, but we are over here down, further down here. Let's stop over here. The focus of this class is to explain the calculations of bridge scour. And typically the way this is done in practice is that there are several formulas. I have chosen to present the most popular, the widely accepted formulas. Among them, the HEC or HEC 18 Federal Highway Administration formula is the one that is most widely accepted. And I do believe it is the one included as part of the model, the HEC RAS model. So when you use HEC RAS in your practice, and I know if you practice in hydraulics, you will eventually use HEC RAS. It is a very popular model, Army Corps of Engineers. So let's get started here by reiterating on the contraction scour and then the local scour. I must admit that there is a lot of confusion, not a lot, but a bit of confusion in these calculations. I have read extensively or repeatedly the original manual, which I have already discussed with you a week ago, and there's still some confusion, but let's go ahead and try to sort things out. The good thing about this is that the calculators, which I have prepared over the years, I've been doing calculators since the year, 2014. No, I'm sorry. 2004 is the first time we did a calculator. Interestingly, the first calculator we did, I thought it was a challenge, is to convert, and this is going to look somewhat stupid for you, but I thought it was a good challenge, and you need to challenge yourself for something easy at the start in order to get started. So I decided to do a calculator that would convert Roman to Arabic numerals and vice versa, and I did it. And I realized at the time, of course, that the maximum number in the Roman numbers is, I believe, 1388. The Romans only counted to 1388. They couldn't get to 1389 because they didn't have a way of expressing that, which is kind of interesting. But following that, 2005, 2006, and we looked around to develop more calculators. And as a result of 15 years of research and development in this area, our laboratory has developed on the order of 350 calculators for hydraulics and hydrology and also environmental hydrology. Unfortunately, everything has to come to a stop. We are basically coming down or not doing any more visual lab work after I retire. So that will eventually disappear. But I have given the laboratory, as it is, to Professor Sepulveda, who is a Unix expert, and our lab is a Unix lab, or let's say Unix Linux lab. So he will continue the work, but his work is mostly in coastal engineering, so he will not be continuing the hydrology and the hydraulics that I was doing for more than 20 years. So let me go back in here under what we're looking at here. The contraction scour under live bed conditions is calculated using the modified Larsen equation, 1960, which is this equation over here, where Y sub S is the mean depth of contraction scour under live bed. These formulas are, interestingly and unfortunately, empirical, but that's what we have. The reason why we have empirical formulas for scour is because we have no way, the profession has no way of doing a 3-dimensional flow calculation that involves or includes sediment movement. No way. There's only one-dimensional sediment movement. maybe even two. I think that two-dimensional sediment movement must be coming up. I was involved in two-dimensional sediment modeling at the very early part of my career. When I was at Colorado State, we developed a two-dimensional sediment routing model. But then later, I moved from Colorado to California, and things kind of didn't go that way. And I have not done any sediment routing calculation for the last 40 years. But that was the start. So eventually, I think the profession will head into two-dimensional sediment movement and eventually to three-dimensional sediment movement. And we may supersede these equations that are empirical. And why do I say that they're empirical? Because empirical formulas usually are populated by numbers that we can't really justify from theory. Like in this case, we have a 0.86 in there, as you can see. Let me make that a little bigger. Yeah, 0.86, where's that coming from? Well, it came from Larson's work. And Larson is a great person, has a very good reputation. It's a very well-established formula. But there's this formula, and I urge you to, I'm not gonna go over the formula with you. I don't think it's necessary. You have the material in there. You will have to study this for the final exam. Later on, if you have use for this, of course, I recommend that download the syllabus, because eventually the syllabus will disappear. You're not gonna, say 6 months down the road, you're not gonna be able to access this information directly on my site. Of course, if you called me up and said, Professor Ponce, I'm looking for this information, since I know you already, I would give it to you. And I'm not gonna disappear in the next 6 months. But the point is, if I were you, I would play safe and download this information into a disk or something, have it in there, or on the web, online, rather on the cloud, so that you can have it in there, if in case you want to use it. So this is the formula of Larson. It has coefficients and it has exponents. The K1 exponent, right, the exponent K1 is given by this table. And as you can see, empirical coefficients, based on the ratio of V sub star over omega. And V sub star is the shear velocity immediately upstream of the bridge, calculated as such. And omega is the fall velocity of the sediment. And the fall velocity is given by this formula, or rather this graph in here, which can be digitized. Everything that we have on the web that we're calculating these formulas based on graphs, we have already digitized. We have been working on digitization of models, or rather formulas for modeling purposes online 20 years, but throughout 40 years, from the beginning of our career. That was one of the first tools that we developed in order to advance and make progress in digital computation. We call it piecewise linear modeling, which means you have a curve in there, you can put a whole bunch of points in there. How many? Couple hundred points in there, and linearize the whole thing. I guess I could say, a little bit rude, linearize the heck out of the equation. Okay, that is an alternative to the so-called splines. But I don't like the splines, because the splines are not accurate at the ends, while the linearization is accurate throughout the range. So we prefer it. And besides, the splines is something that typically people do not develop. You got to rely on other people. Excel, I believe, has a few functions for splines, but since I typically don't use Excel, I don't know too much about it. Excel is powerful if you know how to use it. So this is the way we calculate the Larson equation, and these are the comments on the Larson equation. So under clear water, we have under clear water also the Larson formula. Note that this formula is dated 1963. And again, Y sub S is the average depth of contraction scour under clear water. Now, the other was, come over here. Yeah, live bed is one and clear water is the other one. Contraction scour under clear water is calculated using the Larson formula, 1963. And again, this formula is also empirical. These formulas have been widely accepted. I guess they are the only formulas So people, if they want to do some modeling for scour, they have to use these formulas. And I presented to you the formulas that are more popular in the US. Local scour. The local scour is one of the most common causes of bridge failure due to hydraulic stress. The following factors must be taken into account in the calculation of local scour in a pier or abutment: the flow rate, the flow depth, the pier width, the discharge intercepted by the abutment and eventually returned to the main channel, right? There's always going to be interceptions of discharge, particularly if there's overflow, return to the main channel. Overflow, how often does overflow occur? That's an interesting question, which we should answer at this point, so as to kind of give you an idea what engineers are faced with. The question is, how often does a river overflow? The answer is, interestingly, from 2 to 5 years. So the channel forming flood has been indicated by the fluvial geomorphologists to be from 2 to 5 years. So that means that every 5 years, you're going to have a flood. A flood meaning a stage that goes above the banks, the local banks. So there's going to be a flood. That's just the way it is. Why is it so often? We can't explain that. That's just the way it is. I didn't develop that number. The geomorphologists know that. The fluvial geomorphologists. There's a whole field of fluvial geomorphology. When I was going to Colorado State, my two major professors were, well, Daryl Simons, Halim Mahmoud, Everett Richardson. I'm going to be talking about those, particularly about Everett Richardson later, hopefully today. And then I also had Stan Shum. There was a professor of geology. He was a fluvial geomorphologist. And in his career, which lasted almost 40 years out there, he wrote about 10 books or more, 10, 12 books. I myself have written 6 books, so I know what to write a book. What does that mean to write a book? So I am kind of surprised and pleased that my professor Sham wrote 12 books. That means he knew what he was talking, and he was very hardworking. Of course, it's not easy to write a book, but that's the point. So we have fluvial geomorphology out there. Discharge intercepted, angle of attack, pier length, size and grain size analysis of the bed material, always important. Condition of the bed, prevailing bed forms, usually during flood, shape of the cross section of the pier or abutment, formation and or transport of ice, and presence of tree trunks and other vegetative debris transported by the flow. Sometimes the flows carry a lot of vegetative debris, and that this could endanger, depending on the quantity, it could endanger the security and safety of the bridge. Some bridges have been hit by logs and have been destroyed, by the way. Not common, but sometimes it does happen. The depth of scour increases directly with the depth and velocity of flow. Therefore, the risk of failure, usually due to an insufficient foundation depth, increases considerably during the passage of an infrequent or extraordinary flood. Insufficient foundation depth. So the foundation should go deep enough so that it's not put in danger or undermined, meaning the scour should not get below the bottom of the foundation. However, whatever type the foundation is, usually piers. But there's also different types of foundations, and the foundation, by the way, is the job of the geotech engineer. I think I already mentioned the other day that when there's the situation of designing a bridge, there's 3 types of professionals in civil engineering that participate. There's the structural engineer, plus the architect, by the way. Some bridges are designed by architects in terms of the looks of the bridge and so forth, the materials. But eventually you have a structural engineer, then a geotech engineer, and a hydraulic engineer, which should be versed on sedimentation. Because you must know by now that not all hydraulic engineers know sedimentation engineering. We are studying sedimentation engineering. I know some of you have taken many of my classes. I've been teaching 4 graduate classes for the last 30 years or so. I think 1995 is when I started teaching my 4th graduate class. So some of you have taken all my classes, or will take all my classes. But not everybody gets into sedimentation. Usually, I would say maybe 5% of the hydraulic engineers know something about sedimentation. So it's a very particular or specialized field, which is kind of good and bad. It's good because it's a good field, but there's not a whole lot of work in it. There's more work in the typical general hydraulics. So there's not that many people dedicated themselves to working on sedimentation engineering. And it is also a difficult subject, as you know, even Einstein acknowledged that. Established formulas for calculating local scour, and we're going to look at them, are HEC 18 from the Federal Highway Administration. But the Federal Highway Administration is just an entity, but they hire out the work. This particular HEC 18 model was originally developed under the auspices or with the participation of my esteemed Professor Everett Richardson back 30, 40 years ago. Subsequently, he participated in the subsequent editions of the HEC 18, and I believe he worked on number 3 and not number 4. Number 4 is dated 2012, and I did not see Everett Richardson's name on the publication dated 2012, which is the one I showed you a week ago. Why is that? Because by 2012, Richardson was already very old. He retired, I believe, in the year 2000, something on that order. As a matter of fact, I happen to know that he passed away that year or the year after. I think it was that year, 2012, is when Professor Richardson passed away. Fortunately, a year before he passed away, he did a video on history of hydraulics at Colorado State. And hopefully today, if we have some time, otherwise Thursday, I will show you that video. It's a short video, short and interesting video. Okay, so we have the HEC 18 equation. The second equation is Jain and Fisher. The third one is Froehlich. I believe the Froehlich equation, Froehlich, I believe, is a person that worked with USGS. I'm not quite sure though. And finally, Melville. I believe Melville originates in Australia. The Melville formula is the most complex or most comprehensive formula for scour. And I think every method points at Melville eventually. We are going to do all 4 calculations, and we're going to do them. I'm going to explain the content, and then we're going to do it online. So you'll have a base to work on later on. And like I said, I do repeat, there are these 4 formulas. They have calculators which were developed by my laboratory over the years. And then there is the HEC RAS formula that has included in it the HEC 18. No relation between HEC RAS and HEC 18, by the way. HEC RAS stands for Hydrologic Engineering Center, the lab, the Army Corps of Engineers lab that was organized or instituted in the year 1968. HEC 18 stands for Hydraulic Engineering Circular, number 18. So if you have a number 18, there must be 17 prior hydraulic engineering circulars. Why the Army Corps? No, that's not the Army Corps. That's the Federal Highway Administration, which is an entirely different agency. Federal Highway Administration is a Department of Transportation, where the Army Corps is with the Army Corps of Engineers, the Defense Department of the United States. So they're different, but they have the same kind of name. They call themselves, their publications and their labs are called the same. HEC 18, HEC RAS. Those are the numbers or the names that we should know in relation to scour calculations. So let's take a look at the famous, because this formula is famous, the HEC 18 formula. The HEC 18 formula calculates the maximum depth of scour in sandy fluvial beds. Very common. Most beds that we care to calculate in practice are sandy fluvial because they're kind of in the middle of the basin. Because by the time you get upstream, it gets rocky, it gets gravelly. And if you get too far or too close to the ocean, it gets silty, because that's just the way Mother Nature put it together. But most cities and towns and so forth are in the middle of the basin. And that's why the bed is typically sandy. There's a correlation, by the way, that can be studied from geomorphology, from fluvial geomorphology, between the slope of the channel bed slope, and the size, the sediment size. And 0.001 is 0.1% is definitely sandy. And it is also subcritical. In order for it to get to critical, it would have to go to 0.004 or 0.005. And by the time it gets there, you're going upstream, getting to be a little gravelly bottom and so forth. So that's not very common. Most rivers are in that range, 0.001, plus minus a certain reasonable range for the slope. And therefore, that is the location where you're going to find sand in the bed, different types of sand. Let's not forget that when Colby did his work in the Niobrara River, in the middle of the country, in Nebraska, he limited the grain sizes from 1 millimeter diameter to 0.1 millimeter diameter, which is in the middle of the sand size. That's what he wanted to do, to look at the sediment transport for the sand sizes. So this is the formula, the HEC 18 formula. As you can see, it has a bunch of coefficients. How were these coefficients calculated? Based on experiments in the laboratory. Physical models in the laboratory were used to develop these formulas. Work, fluid mechanics, theory, and physical models in various laboratories. I don't have the information as to which laboratory contributed what part. Now, this formula, it is my understanding that it has been under progression or development for the last 40, 50 years. Yes, because the report is in its fourth or even fifth release over 50 years. Every 10 years, they decide to update it and put it together in a better way, presumably better way, better written, better presented, and so forth. Although I must confess to you or reveal to you that I personally do not like the way that report is written. That report that I shown you, it is kind of confusing. Confusing, if it's confusing for me, it is confusing for anybody. Excuse me for saying that, but it's the truth. Okay, there's ways to speak clearly and to write clearly. And HEC 18 does not do that, unfortunately. Okay, so this is the formula. Y sub S is the scour depth of scour hole. Y sub 1 is the depth of flow immediately upstream of the pier, indicated in the graph, figure 13 that you see in there. Y sub 1 immediately upstream, and Y sub S is the scour hole. V1 mean velocity, A with pier, as you can see in there, facing the flow, the Fruit number, the case of 1 correction factor to take into account the shape of the cross section in figure 14 and table 2. Case of 2, correction factor to take into account the effect of the angle theta between the alignment of the pier and the alignment of the flow. That means the angle of the so-called angle of attack of the flow. In case of 2 is this formula. In case of 3 is a correction factor to take into account the condition of the fluvial bed. And these are the typical forms of the cross section of a bridge pier. All this information is taken, of course, from the manuals and the documents, official documents that present the theory and the practice of HEC 18. So you can see the correction factor in here, figure 14 for the various types of piers, correction factor K2. Now, which piers do we choose? That's the structural engineer and the architect get together. What is the role of one vis-a-vis the other? To be honest with you, I don't know precisely. But what I know is that typically in the issue of a function of any structure, architects get involved. But in the issue of the strength and stability, engineers get involved. So the architects don't get involved on the strength or stability. They don't, that's not their job. While engineers, the structural engineers, typically don't get involved in the function or the looks and stuff like that. Although there are some smaller projects in which the engineer does the whole thing. The architect does not get involved. The opposite, I don't think I'm going to say that, but I think I would be stretching my knowledge if I said that some bridges were designed only by architects. I do not believe that is the case. Okay, so architects have important roles in the design, but they're not alone. They're usually with the engineers. Well, I mean, if you go back with history, and I've looked at history, I'm a student of history. 500 years ago, there were no engineers. They were all architects. The Roman architects, right? Of the Roman architects. I mean, the history shows the Roman architects, the architect of the aqueducts of Rome and the building of Rome and so forth. So when is it that the name engineering developed? I read that. I know this topic. It was in 1753. There was an engineer, a military engineer in France that found himself working on civilian projects. And he started calling himself civilian engineer. And that pretty soon was shortened to civil engineer. 1753 is the beginning of our profession as such. So who were the first engineers? Not the civils. The first engineers were the military. They were the ones in charge of blowing up the bridges or putting up a bridge in a very ready or quick time. during war. So there was the military engineers, then the civil engineers, 1753, and they were followed by the mechanical engineers after the Industrial Revolution. The mechanical engineers came about. And then 100 years later, you have the electrical engineers and all the other engineers. Okay, so now let's go back in here. The correction factor, this table 2, the correction factor, table 3, correction factor K1 and K2. All these, by the way, have been put into the calculators. So when you use the calculators, you don't have to look at these tables. That's old stuff. We put it all in the calculator, right? However, I must say this, that if you use a calculator, I don't care which calculator, you could use Professor Ponce's calculator or any other calculator, and there must be some calculators out there. Although I don't have any interest in checking that stuff. I'm not in that business of comparing calculators from various vendors or suppliers. But I have a hunch that not too many people are using these calculators, people are using them, are developing these calculators. There are not too many people, I don't know why. But I've been doing this for, as I told you, 2004, that's 18 years. And we don't see too many people following us. There might be a few out there, less than 5, something like that. So, but the point is that if you have to do a calculator or do this calculation, you could do one of several things. The first one is to use HEC RAS and use HEC 18, which is part of HEC RAS. And that's official. You don't have to touch it. They would not allow you to touch HEC RAS. What do I mean? You can touch it on the surface, you can run it, but you can't explore it. You cannot open up HEC RAS to examine it. They won't let you. They will not give you the source code. The Army Corps will not give you the source code. The only thing you could touch is the source code if you wanted to and if you were able to touch, but you cannot. They won't give it to you. So all you can do is run the model, input, output. I put this input and I get this output, right? If the model is wrong, you won't be able to tell. But a 99.9% it will not be wrong. It's been tested substantially by the Army Corps of Engineers. The reputation is on the line, and typically these models are not in error. I'm talking about gross errors. Okay, so you can trust, and besides, you don't even have to trust. All you have to say is that's the Army Corps of Engineers model, and I use that. But if you don't want to do that, or you can't, or you're in some other country out there, and the Army Corps is not necessarily ruling out there in the various, and you wanted to do some scour calculations. Well, you could look at all the formulas and do your hand calculations based on the tables. And that's why we're giving you the tables, which, by the way, are part of the manuals. All the manuals have the tables. I did not invent these tables. I'm copying the tables. And then you have 2 routes. You either develop a spreadsheet and put everything in the spreadsheet. And the good thing about that is that's yours. You have confidence in it, and you can use it repeatedly. I don't think you can share it. It's difficult to share. You can give it to your friends if you want to, but typically people don't do that, because spreadsheets are like personal, right? So you have your spreadsheet, you can do that, and it can be done. It's been done, I'm sure. There's a lot of people that exclusively work with spreadsheets out there, by the way. That's one thing. The other thing you could do is use Professor Ponce's calculator. Sure, why not? As long as Professor Ponce is alive or whatever. I said that jokingly, but it's really not jokingly, because my time is passing, and I, maybe 5 to 10 years down the road, I may not be here. That is a fact. Nobody knows when, but that's going to happen. So say 10 years down the road, you want to do a scour calculation, and you look for Professor Ponce's calculator that you learned in this class, and it's not there. Okay, but if it's there, or if it's not 10 years, they say tomorrow or the next year, it'll be there still, and then you can run it. But if I were you, I would do this. I would do a hand calculation of Professor Ponce's calculator to make sure that he's correct, because he could be wrong, and he's not official anyway, right? But once you prove that your calculation is exactly the same as Professor Ponce's in his visual lab, then every judicious judgment, or every judgment would tell you, go ahead, you already verified it, and you can use it repeatedly. Same thing, okay? And that has happened, by the way. I have had, every once in a while, like I said twice in my history of 18 years of calculations, that I had people straighten me out, call me and say, hey, you made a mistake. And I have corrected the mistake, and thank profusely the people that said that. or that acknowledged, or rather advised me that I had made a mistake. In order to do that, you know what that means. It means you got to understand the procedure, and then you got to check it by some other means, usually Excel, by the way, and then tell whoever is the author of that program that he or she is wrong. One thing that I should tell you at this point, perhaps you do not know, is that there's quite a difference between Excel and the calculators that we use in accuracy, because Excel typically does not do a whole lot of calculations. But that's a secondary point. Typically, the accuracy is very close to each other. So that's what I'm going to say at this point. So you get the calculator. So we are going to be using the calculators. As a matter of fact, we're going to do a calculation right now of the online scour HEC 18. Online scour HEC 18. Given flow depth, y is a 1, 2 meters, flow velocity v is a 1, 3 meters per second, pier width A equal 0.5 meters, pier width length equal 2 meters, angle of attack of the flow 0, square nose pier shape, and 7 plain bed with anti-dunes. Calculate HEC 18. So that's what we're going to do now, calculate by HEC 18. So this morning I was looking at this and I put the numbers in here. Hopefully, what did we say? Square nose, right? I believe we say square nose. And plain bed and anti-dune flow, right? And we do the calculation and we get 1.66. Hold it there. Yeah, 1.66. So it's correct. We reproduce the calculation that is shown in the paper. It's correct. You can play around with this to get some answers. Actually, I've actually used the same data in the 3 formulas, and 2 of them came exactly the same, and the other one kind of diverged a little bit. Because, as we already know, that not all the formulas are going to give you the same answer. They were different. They were developed in different ways and so forth. And sedimentation, it's just like that. There's variations in the calculations. So the next formula that we have is the Jain and Fisher formula, applicable to the calculation of local scour. The formula distinguishes between 2 types of scour. Scouring under clear water conditions for low fruit numbers, and scouring under live bed conditions for high fruit numbers. This is one of the things I to be honest with you, I quite don't understand. Typically, the scour must be under usually live bed conditions, because you scour and fail a bridge under high fruit numbers, not under low fruit numbers. Unless I'm mistaken here, based on my experience, this is what happens. The flow starts going through the bridge doesn't have a cross section, the flow is being forced to go through the bridge, therefore the fruit number increases. And so therefore the live bed condition is probably a more typical condition. Okay, the formulas are the following. Here are the formulas. Again, empirical formulas by Jain and Fisher. Where did the 184, where did it come from, right? And the coefficients, but that's it. That's the status, the state of the art in scour calculations, empirical formulas. Scour under clear water, scour under live bed. For the case, this is a limiting case, F minus F sub C. F is the fruit number and F sub C is the critical fruit number, which is calculated based on the critical velocity. So we're having here, and we also have the critical velocity calculated by this formula, which we already have explained this formula, and that's the reason why we have equation 6, equation 7, and then equation 1. So that's not a mistake in the numbering. The equation 1 has already been discussed in this particular paper, and that's why we felt that we should not rename so as to reduce the confusion. So this equation has already been explained. So now we have the online calculation of the Jain and Fisher. So let's go ahead and do this calculation. Jain and Fisher. Metric units, the y is 2, the velocity is 3, and the pier width is 0.5, and the mean diameter is 1, right? And we do the calculation, and this came out to be 169. The other one, I believe, was 166. So there is a surprising, very good accuracy or correspondence between these 2 formulas, the HEC 18 and the Jain and Fisher. Froehlich formula. The Froehlich formula, Froehlich, I think it's Froehlich. So I believe it's a German. I'm not sure. Looks German in terms of the origin of the last name. Formula is frequently used for the calculation of local scour in a bridge pier. The version of the formula applicable for design is, and look at this formula, Fascinating, interesting, and fully and totally empirical. Look at these numbers, 0.62, 0.2, 0.46. These are all correlations, multiple correlations that were done based on data. I am not sure, because I have not examined these formulas extensively, if these formulas are based on field data or laboratory data. My guess is that probably both, but I cannot for sure certainly explain to all of you or explain to you all the details of how these formulas were put together. Not even the manuals have it, and I'm basing my information on the manuals, particularly the HEC 18 manual. So we have in here the version of the formula is equation 8 for y sub s is scour depth, that's the same thing. And then the rest of the parameters that you see in here, phi is a dimensionless coefficient, which accounts for the form of the cross section. Phi equal 1.3 for square nose, 1 for round nose, and 0.7 for sharp nose. Then velocity v sub 1, y1 flow depth immediately upstream of the pier, and fruit number 1, fruit number immediately upstream of the pier. And we have an equation in here. I pulled out an equation from the web, detail of Petty Creek Road Bridge Pier on the Clark River near Alberton, Montana. As you know, there's millions, I wouldn't put a million, but there's thousands, hundreds of thousands of bridges throughout the United States, bridges that are under, that are used to cross rivers. So there's a lot of situations like this. This is just an example of that I pulled out from a report of a bridge scour. Okay, so we have an example in here, evaluation of Froehlich's design formula. This is a part of the report that I have consulted in order to put together this report or this paper. Calculated pier scour and measured pier scour. So if in the 45-degree angle, there's correspondence, right? So the calculated, no, the way to read this, so the calculated was 4 and the measured was 2. That's the way it was. So the calculated is a lot higher in here. Most of the calculated were higher, which is kind of good because, I mean, it gives you a sense of security. The calculated actually greater than the measured. This is just one example to determine the relative accuracy of these formulas. Comparison done by the developers of the formulas. So finally, we're going to do again a calculation of this formula in here. It's all prepared in here. Flow depth 2 meters, flow velocity 3 meters, pier width 0.5, angle of attack. Okay, so I'm going to go ahead and do this. Units metric, flow depth 2 meters, flow velocity 3 meters, pier width 0.5, angle of attack 0, mean diameter 1, and what was it? Did we have any indication? I forgot about that. And square nose pier. So square nose pier. Okay, there we go. 1.09. Note that the data over here, none of these formulas require the same data. Why is that? Because they were all done by different groups of people, different researchers. They looked at different things. They emphasized what each one of those groups wanted to emphasize. So they came up with different sets of data. If they had the same set of data, they could be comparable, right? They can be compared on a one-to-one basis. But since they all have different data, they're not really comparable. So all we can say is that they give you different answers. Now, we ran 3 of these. The first one came 1.66, the second one 1.66, and the third one 1.09 or 1.10. So that leads us to the conclusion that for similar data, I'm not going to say the same, similar data, the Froehlich formula gives a smaller answer right here. We demonstrated. It's demonstrated now. It gives the smaller answer. Which, I mean, if we are faced with design, which one are we going to use? Well, that depends on the experience of the designers. I am sure that I am not a bridge scour designer, although I have done 2 or 3 calculations throughout the course of my career. We did the calculation, specific calculation on the Valle de Guadalupe River 10 years ago. We had a job there. So that's perhaps 1 or 2 that I've done, which is kind of, we conclude that Professor Ponce is not an expert on scour. I think I already said that. Although I know the formulas and I can talk about it in somewhat an intelligent fashion. But in order to do this calculation, people that are hired to do these calculations have usually done 50 or 100 of them. So they know more or less what they're doing based on experience, right? So the designers would have perhaps a preferred formula, or perhaps they will use an average of the 2 or 3 formulas that they're working with. And perhaps they would also include the factor of safety on the design. Why is that? I think it merits that we discuss that at this point. In structural engineering, the typical practice requires a factor of safety because there's a lot of uncertainties. And there's 2 factors of safety, one on the load and one on the material. So if the material has X strength, you would put in there the load should be 1/3 of the 1/3, because typically the factor of safety is 3, and the load the same. So in typical structural design, there's a factor of safety of 3 on the material and 3 on the load. So by the time you multiply both, you get a factor of safety of 9. And that's the reason why buildings don't fall apart or fall under their own weight. Do buildings fail? The answer is yes. But I mean, how many buildings are there throughout the world? Millions. And building failures are rare. I remember a story, I think it was in Spain many years ago, maybe 20 years ago. A department store announced the sale of a couple of sofas that were cost $300, and they were going to sell them to the first, they had 2. They were going to sell them to the first 2 customers who came over Monday morning at 9 o'clock. They were going to open the store and they were going to sell them for $10. I believe those are the correct figures. By the way, this is all on the web. It can be consulted. So they had a multitude of people, maybe a couple hundred of them, or perhaps more, that showed up to claim the $10 sofa. And they rushed into the second floor. Can you imagine that? A couple hundred people, and the floor collapsed. There were people dead. Why? That was the issue of live load and dead load and so forth. How funny, dead load. There were a lot of people dead because they exceeded, that particular charge exceeded the design of that particular floor, right? Not only static, but also dynamic. So that was a disaster, a failure, and it was sad. Another example like that happened in, I believe, Kansas City, the Kansas City Hyatt, maybe 20, 25 years ago. The situation more or less was this. They had a walkway in the lobby, and the walkway was just a design walkway, right? But somebody organized a party over there, and there were 300-400 people in the lobby, and many of them decided to, because I guess there was lack of space. I wasn't there. I wasn't there, but I read about it. There's a very classical story of failure. So a bunch of people, maybe 150 people that were in the lobby, climbed on the walkway, and they were dancing actively and so forth, making a lot of noise. And then the walkway collapsed, and many people were killed, because not only it collapsed, the people that were on top, but there were people at the bottom too, below the walkway. So it was a mess. This is the Hyatt Regency failure, Kansas City, I believe, maybe 20, 25 years ago. Classical example of structural failure. Subsequent studies revealed that there was a change order when they built the stuff, and the actual factor of safety got reduced by half. I can't explain to you, I'm not a structural engineer, cannot explain to you the actual details, but I read the reports, and the reports say there was a bug, there was an error in the construction, not in the design, in the construction. And they reduced the factor of safety by half. So if the factor of safety was 9, it got reduced to 4, and by the time 300 people, which were not expected, started dancing on the walkway, the factor of safety of 4 came down to 1, and that was the end of the walkway, right? So it does happen. So, but in hydraulic engineering, we don't go by factor of safety, we go by frequency. So it's a kind of an esoteric, different way of approaching it. We typically don't talk about factor of safety in hydraulic engineering. Our factor of safety is the frequency. So if you choose a 100-year frequency for the flood, for the velocity, that is more risky than 500-year frequency, because a 500-year frequency will be a higher load, right? If you design for a higher load, you're safer as far as the structure is concerned. So we use the factor of safety. Typically, I already said that, 500-year return period. Assumes, of course, that the flood, subject of the calculation, is going to happen once every 500 years. It does not mean that it will take 500 years to happen. No. Technically, what it means is that if it does happen tomorrow, it will take another 500 years to repeat itself, the size of that event. But it can happen tomorrow. So that's why there are failures in hydraulic engineering, because we're unlucky. I chose 500 years and all of a sudden the event happened tomorrow. That is unlucky. Why do we choose 500 years? Why don't we choose forever? Impossible. That's too costly. I already explained that. It used to be 100 years, but we had so many failures, particularly scour failures, that it was upped. Maybe 5-10 years ago, it was up to, it was increased to 500. And now 500 is the norm. I think that's been said in the manual. So it depends. Now you could go to 1,000. You could go to 1,000 as a designer. You could go to 1,000, but that has to be a conversation between you and the owner. Typically, you're not the owner. You're the guy that is doing the design, but that's not the owner. The owner is the guy that has the bucks, and he's hiring you to do the design, right? So you have to have a conversation. You as a designer have to have a conversation with the owner and explain to him or her that you would like this bridge to be very safe, and you prefer to use 1,000 than 500, which is the norm. And they'll have to agree. Why they'll have to agree? Because it is their money that is on the front, on the line. They're going to pay for the bridge. You're going to say, well, if it's a 500, it's going to cost X, and it's a 1,000, it's going to cost 1.5X. Can you pay for it? Right? That's the way it's done. So we have covered 3 formulas: HEC 18, Jain and Fisher, and Froehlich. Now we're going to end up with the most comprehensive formula, which is the Melville formula, considered to be the most comprehensive formula. Melville, I believe, because I looked extensively into his publication, which is dated, I believe, the year 1998. I could be wrong in here. Let me just see. Maybe I know I don't have. No, this is a paper that doesn't. This is a web publication. So since it's a web publication, it doesn't have any references. But we can go to the references. Let's do that. Let's do that. Pier and abutment scour using Melville equation. Here it is. 1997. This is the paper which is the basis for what I'm going to say right now in the next 15 minutes. Pier and abutment scour integrated approach. So if you really want to look at what Melville did, you got to go here. You got to hold of the original source. Hopefully we have done a good job of reproducing what he said. It is very complex. Okay, I am told, because I researched this, that Melville spent 20 years developing this equation. He is a senior lecturer, Department of Civil and Resources Engineering, University of Auckland, New Zealand. Oh, I'm sorry, I said Australia. No, it's New Zealand. Different. Australia is not the same as New Zealand. Okay, so he's a senior lecturer. Senior lecturer doesn't sound like a whole lot here in the United States, but I believe in Australia it does. He's an important person out there. With that title, senior lecturer, he would be a non-important person here in the United States, but that's not the United States. So I have presented to you the paper by Melville, the origination of the paper, the original version of the paper by Melville. So now we're going to dwell into the details of the model. So Melville's formula calculates the maximum depth of local scour on a bridge pier or abutment. So it does pier or abutments. So now what we're going to do is I'm going to go over the formula to kind of show you the complexity of what Melville did in 1997. So that's 25 years ago. And to be honest with you, I don't know if this gentleman is still alive. I honestly don't know. I would have to research it. But at the time, he was very well known, and he's widely respected and recognized as developing a formula for local scour, which is the most comprehensive. And you will see that it is, in fact, the most comprehensive, the one that takes into account more factors or conditions. So the formula is based on a product of 6 empirical variables K, each of which evaluates a contributing factor to local scour. This reminds me, at least me, if not you guys, of the universal soil loss equation. I know some of you are talking about that at the end of this class. Universal soil loss equation, the Russell, the Muscle, the 6 empirical case, right? In the same thinking here. So this is a practice that is not uncommon. The formula is depth of scour, local scour. Case of YW, case of I, case of D, case of S, case of theta, case of G. All these cases have specific meanings, and the subscripts relate to specific meanings. It is confusing. It's a little bit confusing. If I had done this, I would have clarified it a little better. But no, I didn't do it. They did it. Oh, Melville did it. It is confusing. So when you read through this for your study that you're going to do later, keep in mind that this was developed by Melville, and he made it in a somewhat confusing fashion. Okay, so we have in here maximum depth of local scour in units of length. Case of YW, it's a depth factor. It has 2 angles. Case of YB for piers, for the width of the pier is a B, or case of YL for abutments, because the width of the abutment, the length of the abutment is L. Width B for piers, length L for abutments in units of length. Factor of flow intensity. Case of I, flow intensity with capital, including effects of sediment gradation and flow velocity. Dimensionless, all dimensionless. So the depth comes from the case of YW, which is in meters or feet. So let's then look at the depth factor. So the depth factor is the first factor. So there's 6 factors. The first factor is the depth factor, and it's covered over here. From line to line, from ruler to ruler. The ruler is the name for the HTML code. The depth factor for piers or abutments. The depth factor case of YW. And what's the W? What's the W doing in there? Because it's relating to width. The width of the width B of the piers, or L of the abutments. Width or length, actually. That's the confusion. That is the confusion. The naming confusion. But so be it. That is his formula. I can't change it. If I change it, it will be a mess. Nobody will understand it. So I have to keep strict reliance on what he said in his paper that I have already shown you, given by one of the following equations. For narrow piers, for intermediate piers, for wide piers, case of YB, case of YB, case of YB, and for short abutments, for intermediate abutments, for long abutments, case of YL, case of YL, case of YL. These are all formulas. Okay, I should tell you that back in the year 2009, I had a student that came to me to work with me. I believe the situation was that it was a lady. She had to do a special study in order to graduate. And so I said, I know what you're going to have to do. Yeah, I'm going to give you the Melville paper, which I already shown you. I gave it to her. I said, here's the Melville paper. You develop a calculator. And she said, well, I don't know how to do it. I said, well, I'm going to teach you. I wanted her to do it because, it's a learning exercise. So she spent 4 months doing this calculator that I'm going to use later on. And it's a good calculator. We tested it and it works really well on the Melville formula. It is the first calculator. I'm not sure, to be honest with you. I shouldn't say. It is one calculator. But honestly, I don't believe that. I already told you earlier that not that many people are actually manufacturing these calculators or making these calculators. So I think I can safely say that there's probably the case that there's no other calculator of the Melville formula. Calculations, yes, but calculator online, I doubt it. So this is the formula, and this is a lot of conditions, if and then. So the calculator itself gets to be very complex. I think I gave it to her because I felt at the time that not only she was going to learn, but also I didn't want to do it. It was too complex. So I figured you can do it and then I'll review it. And reviewing is not the same as doing it. So anyway, so that's the first one. No, that's the first one. The depth factor. That gives it the depth. Flow intensity. All the other factors are dimensionless. Okay, the flow intensity factor necessary to distinguish between 2 types of local scour, under clear water and under live bed. Scouring under clear water typically occurs in the floodplain. Scouring under live bed occurs when there is sediment transport in the vicinity of the hull. If the sediment is uniform, that is with a gradation coefficient sigma sub G less than 1.3, less than or equal to 1.3, armoring is not produced. Armoring is the erosion of the finer portions of the sediment bed, leaving the larger portions behind, and then they eventually armor the bed. You don't remove all the sediment, but the sediment has technically been already protected against subsequent or additional erosion by the concept of armoring. Okay, if the sediment is non-uniform with a gradation coefficient sigma sub g greater than 1.3, armoring is effectively produced, which reduces the depth of the scour hole. And then we define what the gradation coefficient is. Sigma sub g equal D84, 84% finer, over D16, 16% finer, to the 1/2 power. The flow intensity factor is given by the following equations. And here we go again. Relations. If and then relations, 12a and 12b. And more conditions, by the way. So to program this equation was a job. When you do this kind of work, you have to basically do a hand calculation following so that you make sure that all the logic inside the program is correct. Velocities V sub C and V sub CA, okay, there are differences between V sub C, which is a mean flow velocity at the onset of bed movement, and V sub CA, the mean flow velocity beyond which armoring of a non-uniform sediment bed is impossible. As you can see, this is not easy. There's all kinds of conditions in here. For quartz sediment at a temperature of T 12 degrees Celsius, the shear velocities are estimated as follows. And there's all kinds of equations in here, and ifs and buts. U sub C for diameters, for two types of diameters, 15 A and B, and 16 A and B. 15 is for U sub star C, and 16 is for U sub star CA, where CA relates to over here, the CA, mean flow velocity beyond which armoring of a non-uniform bed sediment is impossible. Okay, so we got this equation. Now we move on to the factor of sediment size. The factor of sediment size is given by one of the following equations. And that's it, the same thing. I'm not going to proceed in here because I'm kind of boring you to death here with all these equations. Believe me, this is tough. It's not easy. There's just so many relations. Interestingly, though, these are all done in the calculation, in the calculator. The lady already spent her time, 4 months, doing this kind of work, putting it all together. Factor of shape of the pier, and these are the pier types, abutment types, and then the factor of alignment of the pier, and so forth. The factor of K sub G, no, not K sub G, K sub theta, K sub theta, alignment factor K sub theta, all in there. Factor of geometry, the geometry of the canal. This doesn't get any more complex than this, by the way. Spatially complex, mathematically complex, logistically complex. But it is purported to be the best formula, the most complete formula for scour calculations. That's why we decided to go after it. Because I realized at the time that nobody was going to do it. We were the only people who could do it. And why could we do it? Because we've done hundreds of these. We know how to do it. It's easy for us. So finally, we stopped there. And when I come back on Thursday, the first thing I'm going to do is I'm going to run a calculation of the Melville equation with the calculator. So let's finish in here. I got 5 minutes, 7 minutes, right? So let's finish in here with this section, unconventional stream crossings. And I'm going to go a little fast in here. But we classify the rivers into perennial, intermittent, and ephemeral. And we have in here pictures. Indian Creek in California. I was in California, Northern California, on a project in the year 1990. The Gila River, I was in Arizona to visit the Welton Mohawk project, and I took a picture of the Gila River, which always interested me because one of my first jobs as a hydrologist, hydrologic engineer, was in the Santa Cruz, which is a tributary of the Gila in Arizona. Rosarito Creek, we did a project in Rosarito Creek, maybe 20 years ago. And then the Mojave River. I was not on a project in the Mojave River. I went there for some social engagement, and I ran into the Mojave River, which I already discussed with you and explained to you after the flood that breached and destroyed the ford on the Mojave. I've shown you this picture already. And I think I already shown you the picture of the Santa Catarina River, which is a suspended a bridge suspended on one side that was built by choice of the engineers, the people in charge, even though it cost more than 2.5 times more money, the cost of the bridge than a conventional doubly supported or supported on both sides. They decided to do this because they had money. The people in Monterey, they have money. It's a very rich city because it is an industrial city. There's a lot of taxes and so forth. So that's the over Santa Catarina River in Monterey. I believe I did tell you that we did a calculation at the time of the capacity of this river, and it turned out to be 6,500 cubic meters per second. And the river was full in the year 1988. There's a picture of the flow of that river, which I have used variously. I don't have it here. I may bring it up and show it to you next Thursday so you can see it. Oh, this Thursday. The ford crossing. The fords have always kind of interested me. It's an easy way to go across a river. This ford I ran into when I was in Brazil in the year 1993, purported to be the longest, or rather the largest ford in the world. But that was just propaganda of the Brazilians. They always like to say, we have the largest. You know, we have the Amazon rainforest, the largest rainforest in the world. But this is not the largest. So this is constructed ford. This is on the Yaguaribira River. On the Yaguaribira is a town, and it's on the Yaguaribe River in the Ceará. I was studying droughts out there in Brazil, and went on a field trip to examine the field situation and ran into this ford. That was in 1993. This one is a ford in Guadalupe Creek. I did an extensive study of Guadalupe Creek in the year 2012. Complete everything. We covered everything. And we, of course, took this picture. This is one of the largest operating fords that I have seen. This is a ford. It's sitting on the ground. In other words, when it floods, it's not. You can't go through. It's risky to go through when there's a flood. But when is there a flood? Oh, there's a flood in here every 5 years, and it goes in a couple of days and it's gone. So these people didn't feel that it was necessary for them to build a bridge. Actually, if you see on the right, they were building a bridge and then they ran out of will for some reason. I don't know why they abandoned that other bridge, but they didn't do it. You can see there, it's an incomplete bridge. This is a fascinating story, also in Mexico. This is an aerial view of the El Gileño Diversion Dam on the Rio Grande de Santiago. The Rio Grande de Santiago is one of the largest rivers in Mexico. This is in Nayarit, in north of Mexico City on the west coast, Nayarit, Mexico. And this is El Gileño Diversion Dam. It is a diversion dam. So what's the story about this dam? Well, the width of the river is this. This is the width of the river over here. But the engineers decided that they were going to extend the width of the river more than twice so that they could put a dam over there and reduce the stage, reduce the depth of flow so that they could have it as a ford. They weren't going to build a bridge over this river. So this is a river that was expanded in order to build a ford and a dam, a ford and a dam. So they're holding water in here, they're releasing the dam. So this is a dam and a ford at the same time. That's fascinating because I honestly do not know of any other in my practice. I didn't cover all the world, of course. So what happens in here is that when the river is flowing, and this is a large river, this is not a dry area, it's a wet area. So there's always flow in there. But interestingly, upstream, there's a dam that regulates the flow through this dam over here. So they hardly ever have too high a flow that would not allow vehicles to go through the bridge, which is a ford. As you can see, there's a vehicle in there going through. This is the ford on Indian and the Mojave River in the flood of 2005, when it was starting to breach, and then a day later, or no, actually, a couple of weeks later, because I took this picture. I did not take this picture. This picture was taken by a neighbor in the area. She had a house a couple of blocks from the location, Linda Hoover, and she's the one that shared with me these pictures. I've shown you these pictures before already. So this is the intersection a couple months later, I believe. I was there in June, and the flood was in March. The Arizona crossing, interestingly used in the Western United States, Arizona, in California. This is a bridge and at the same time a ford. Yes, it is a bridge and a ford, because you could have flow there under culverts, but if this thing flows high, it'll go over and it's supposed to operate fine. It's supposed to operate fine. It's not being destroyed by overflow. By the way, I kind of the last couple of years, I discovered one of these over in Escondido. There's a park in Escondido. I don't remember the name right now. But if you want to go out there and visit it, you can, because it's very close. So from where I am, it's about 15 minutes to head to this crossing, Arizona crossing in Escondido. It's a very popular way of dealing with rivers where you don't know what the flow is going to be. It could be nothing or it could be a whole lot. So this is a good design. Likewise, in Mexico, we have the same thing. This is Tecate Creek. And finally, one of my developments, my invention is the Ford Bridge, which is on a wide river. I'm going to use 2 minutes in here to finish. On a wide river, you cannot have a long bridge because it will be too costly. There's not enough traffic in there. So what could be done is this. With a bridge that will handle the 2-year flood frequency and operate it as a ford when you have the 100-year frequency or greater frequency than 100. So the ford's over here, the bridge over here. So this is what we call the Ford Bridge. And I thought in my ignorance that I had developed the idea that you could combine a ford and a bridge. Because subsequently, about several years ago, 3 or 4 years ago, I had something to do in Sinaloa, Guasave, Sinaloa. I have a friend over there and I visited him for a couple of days. And sure enough, I ran into a Ford Bridge. So I was really kind of disappointed. I was not the original inventor of the Ford Bridge. The Mexicans had already done it. Why do I know that? Well, I mean, I know Spanish. Puente Vado over here means Ford Bridge. Vado is ford and puente is bridge. So this is a Puente Vado. This operated, like I'm saying, you could have flow under the bridge or flow over the bridge also, because the bridge was made strong enough to sustain flow over the bridge, like a vado, right? Like a ford, exactly. A ford is a vado in Spanish, okay? So that was interesting. And finally, longevity of a bridge. Can be concluded that give me a minute here. Longevity of a bridge depends on whether its build strength respect the hydraulic integrity of the river. For instance, we have the Roman bridge over the Guadiana River in Merida, Spain, which is built 2,000 years ago by the Romans. Currently, it's not operated. It's operated as a pedestrian bridge, so people have to walk a whole lot. You can cycle out there, or motorcycle, or whatever. But this bridge was built by the Romans 2,000 years ago, and it's still there. Why? Because it did not encroach on the width of the bridge. There's no encroachment out there. They went from the beginning to the end of the bridge. They just let the water go through, and it's still there 2,000 years later. Should we do this like the Romans? And the answer is no, we don't build like the Romans. We built for 200 years, 500 years. The Romans were building presumably forever, and they're still there 2,000 years later. That's another picture that I pulled out of the web. And finally, not only the Romans, we have a bridge here in Peru built by the Incas more than 500 years ago, which is still standing because it is not encroaching upon the river. Look and see, it's got about 24 holes in there, or rather openings. 1, 2, 3, start counting them, there's 24 of them. They're not encroaching on the width. As a matter of fact, they're making the water, whatever it is, go through. And one of the good things about this bridge, which has allowed it to last for so long, technically more than 500 years, it could be 700 years, something on that order, is that there are very few floods coming through. Very few floods coming through, that's a fact. So it's a flood protected bridge. If it had not been flood protected, it probably would have failed. But why did this river is flood protected? Because it is right below a lake, and the lake attenuates all the floods. So there's no flood, there's no large flood that comes through this river. I mean, through this bridge, and that is why there's more than 500 years. So I'm going to stop there. I'm going to stop there. I covered the ground today. So what we're going to do this Thursday, which is our last class, last session or last period of this class, I'm going to go over the calculator for the Melville formula as an example. And then I'm going to be going into the next chapter, which is on measurements, sediment measurements. So with that, I will say goodbye and see you this Thursday.